Process modeling. In this video, we are going to see about process modeling. Process modeling involves graphically representing the processes or actions that capture, manipulate, store, and distribute data between a system and its environment and among components within a system. A common form of a process model is a data flow diagram, DFD. A data flow diagram is a graphic that illustrates the movement of data between external entities and the processes and data stored within a system. Although several different tools have been developed for process modeling, we focus solely on data flow diagrams because they are useful tools for process modeling. Data flow diagramming is one of several structured analysis techniques used to increase software development productivity. Although not all organizations use each structured analysis technique, collectively these techniques like data flow diagrams have had a significant impact on the quality of the system development process. Modeling a system's process. The analysis team begins the process of structuring requirements with an abundance of information gathered during requirements determination. As part of structuring, you and the other team members must organize the information into a meaningful representation of the information system that exists and of the requirements desired in a replacement system. In addition to modeling the processing elements of an information system and transformation of data in the system, analysts use both process and data models to establish specification of an information system. With a supporting tool such as a case tool, process and data models can also provide the basis for the automatic generation of an information system. Deliverables and outcomes. In structured analysis, the primary deliverables from process modeling are a set of coherent interrelated data flow diagram. The progression of deliverables that result from studying and documenting a system's process. First, a context data flow diagram shows the scope of the system, indicating which elements are inside and outside the system. Second, data flow diagrams of the current system specify which people and technologies are used in the processes to move and transform data, accepting inputs and producing outputs. The detail of these diagrams allows the analyst to understand the current system and eventually to determine how to convert the current system into its replacement. Third, technology-independent or logically data flow diagrams show the data flow structure and functional requirements of the new system. Finally, entries for all of the objects in all diagrams are included in the project dictionary or case repository. This logical progression of deliverables helps to understand the existing system. To reduce this system into its essential elements, to show the way in which the new system should meet its information processing requirements as they were identified during requirements determination. In later steps in the system's development lifecycle, project team members make decisions on exactly how the new system will deliver these new requirements in specific manual and automated functions. Because requirements determination and structuring are often parallel steps, data flow diagrams evolve from the more general to the more detailed as current and replacement systems are better understood. Even though data flow diagrams remain a popular tool for process modeling and can significantly increase software development productivity, they are not used in all systems development methodologies. Some organizations such as EDS have developed their own type of diagrams to model processes. Some methodologies such as Rapid Application Development (RAD) do not model processes separately at all. Instead, RAD builds processes the work or actions that transform data so that they can be stored or distributed into the prototypes created as the core of its development cycle. DFDs illustrate important concepts about the movement of data between manual and automated steps and are a way to depict workflow in an organization. DFDs continue to benefit information system professionals as tools for both analysis and communication. Logical and physical design. In this video, we are going to see about logical and physical design. A data flow diagram (DFD) depicts the data flow in the system and defines its boundaries as well. System design goes through two phases of development, logical and physical. The diagrammatic representation of logical and physical design. The logical design in general is inclusive of the following list. Review the present or existing physical system, its data flows, file contents, volume, etc. Outlines security and control specifications including backup or recovery procedures, file integrity and maintenance, etc. Works out the implementation plan or schedule. Constructs a logical design walkthrough of the flow of information, output, input controls, and the implementation plan. Provides for an audit at irregular intervals of time. The physical design of a system is a natural corollary to its logical design. It produces the working system by defining the design specification that inform the programmers as to what exactly the system must perform. Produces the report on a printer or displays it on screen while maintaining and update data at all times. Physical design essentially consists of the following steps. Design the physical system. Specify input-output media. Design the database or file structures. Specify backup recovery procedures. Design physical information flow through the system. Plan system implementation. Prepare a conversion schedule and target dates. Prepare training procedures, courses, classes, etc. Devise a test plan and specify any new hardware or software requirements. Update costs, benefits, conversion dates, and system constraints such as legal, financial, operating system, etc. Conceptual data modeling. In this video, we are going to see about conceptual data modeling. Conceptual data model includes all major entities in relationship and does not contain much detailed level of information about attributes and is often used in the initial planning phase. Conceptual data model is created by gathering business requirements from various sources like business documents, discussion with functional teams, business analysts, smart management experts, and end users who do the reporting on the database. Data modelers create conceptual data model and forward that model to functional team for their review. Conceptual data model highlights. CDM is the first step in constructing a data model in top-down approach and is a clear and accurate visual representation of the business of an organization. CDM visualizes the overall structure of the database and provides high-level information about the subject areas or data structures of an organization. CDM comprises of entity types and relationships. The relationship between the subject areas and the relationship between each entity in a subject area are drawn by symbolic notation IDEF1X or IE. In a data model, cardinality represents the relationship between two entities, that is one-to-one relationship or one-to-many relationship or many-to-many relationship between the entities. CDM contains data structures that have not been implemented in the database. In CDM discussion, technical as well as non-technical team projects their ideas for building a second logical data model. In example diagram below, conceptual data model contains major entities from savings, credit card, investment, and loans. Conceptual data modeling gives an idea to the functional and technical team about how business requirements would be projected in the logical data model. Figure is a representation of conceptual data modeling. Entity relationship analysis. In this video, we are going to see about entity relationship analysis. The relational in the name relational databases refers to the fact that different tables relate to each other via keys and to the fact that columns in a given row relate to the values for that column. For instance, a zip code column in any table can link, that is relate, to the zip code table. The key makes it possible to look up information available in the zip code table. For instance, this entity relationship diagram shows the relationship among entities in the purchase dataset. Each entity corresponds to one table. These relationships have a characteristic called cardinality, which is the number of items related on each side. For instance, the relationship between orders and zip census is a 0 or one-to-many relationship. This specifies that for every row in orders, there is at most one zip code, and every zip code has 0, 1 or more orders. A foreign key is just a column whose contents are the primary key of another table. Zip code in orders is a foreign key. Zip code in zip census is a primary key. To indicate that there is no match, the foreign key column could be nullable or contain a default missing value such as 00000, which would indicate an invalid zip code. There are some other interesting relationships between entities. The 0 or one-to-one relationship says that there is at most one match between two tables. This is often a subsetting relationship. Another relationship is a many-to-many relationship. A customer might purchase many different products, and any given product might be purchased by many different customers. In fact, the purchase dataset does not have a many-to-many relationship between orders and products. This relationship is represented by the order line entity, which has a 0 or one-to-many relationship with each of those. Another type of relationship is the one-at-a-time relationship. Entity relationship modeling. In this video, we are going to see about entity relationship modeling. The entity relationship data model (ER) has existed for over 35 years. ER modeling is based on two concepts: entities, that is things, for example Professor BA course database system; relationships, that is associations or interactions between entities, for example Professor teaches course database system. ER models or ER schemas are represented by ER diagrams. We will look at a sample database called the company database to illustrate the concept of entity relationship model. This database contains the information about employees, departments, and projects. There are several departments in the company. Each department has a unique identification, a name, location of the office, and a particular employee who manages the department. A department controls a number of projects, each of which has a unique name, a unique number, and a budget. Each employee has name and identification number, address, salary, birth date. Entity, entity set, and entity type. An entity is an object in the real world with an independent existence and can be differentiated from other projects. An entity might be an object with physical existence, for example, a lecturer, a student, a car. An object with conceptual existence, for example, a course, a job, a position. An entity type defines a collection of similar entities. An entity set is a collection of entities of an entity type at a point of time. In ER diagrams, an entity type is represented by a name in a box. Figure is the diagrammatic representation of entity set. Types of entities. Independent entities, also referred to as kernels, are the backbone of the database. It is what other tables are based on. Kernels have the following characteristics. They are the building blocks of a database. The primary key may be simple or composite. The primary key is not a foreign key. They do not depend on another entity for their existence. Example: customer table, employee table, product table. There are two types of entities such as dependent entities, characteristic entities. Dependent entities. Dependent entities, also referred to as derived, depend on other tables for their meaning. Dependent entities are used to connect two kernels together. Many-to-many relationships become associative tables with at least two foreign keys. There are three options for the primary key. Use a composite of foreign keys of associated tables if unique. Use a composite of foreign keys and qualifying column. Create a new simple primary key. Characteristic entities. Characteristic entities provide more information about another table. These entities have the following characteristic. They represent multivalued attributes. They describe other entities. They typically have a one-to-many relationship. The foreign key is used to further identify the characterized table. Options for primary key are as follows. Foreign key plus a qualifying column. Create a new simple primary key. Employee, EID, name, address, age, salary. Employee phone, EID, phone. Attributes. In this video, we are going to see about attributes. Each entity is described by a set of attributes. For example, employee is equal to name, address, age, salary. Each attribute has a name associated with an entity and is associated with a domain of legal values. In the diagram, each attribute is represented by an oval with a name inside. Types of attributes. There are a few types of attributes you need to be familiar with. Composite attributes, multivalued attributes, derived attributes. Simple attributes are attributes that is drawn from the atomic value domains. For example, name is equal to John, age is equal to 23, also called single valued. The representation of types of attributes. Composite attributes. Composite attributes are attributes that consist of a hierarchy of attributes. Composite attributes are mapped by concatenation or flattering. Concatenating means we keep the composite attributes only, ignore the components of it. Flattering, on the other hand, means including only the simple component attributes of a composite attribute. For example, address may consist of number, street, and suburb gives address is equal to 59 plus Meek Street plus Kingsford. The representation of composite attribute. Multivalued attributes. Multivalued attributes are attributes that have a set of values for each entity. Multivalued attributes are mapped by using additional relation schema. For example, degrees of a person, BSc, MIT, PhD. The diagrammatic representation of multivalued attribute. Derived attributes. Derived attributes are attributes that contain values that are calculated from other attributes. For example, age can be derived from attribute date of birth. In this situation, date of birth might be called stored attribute. Keys. In this video, we are going to see about keys. An important constraint on the entities is the key. The key is an attribute or a group of attributes whose values can be used to uniquely identify an individual entity in an entity set. There are several keys in entity relationship modeling, such as candidate key, composite key, primary key, alternate key, foreign key. Candidate key. A simple or composite key that is unique and minimal. Unique is nothing but no two rows in a table may have the same value at any time. Minimal is nothing but every column must be necessary for uniqueness. For example, for the entity employee, EID, first name, last name, SIN, address, phone, birth date, salary, department ID. Possible candidate keys are EID, SIN. First name and last name, assuming there is no one else in the company with the same name. Last name and department ID, assuming two people with the same last name don't work in the same department. EID, SIN are also candidate keys. Composite key, composed of more than one attribute. For example, first name and last name, assuming there is no one else in the company with the same name. Last name and department ID, assuming two people with the same last name don't work in the same department. A composite key can have two or more attributes, but it must be minimal. Primary key. A candidate key is selected by the designer to uniquely identify tuples in a table. It must not be null. A key is chosen by the database designer to be used as an identifying mechanism for the whole entity set. This is referred to as the primary key. This key is indicated by underlining the attribute in the ER model. For example, employee, EID, first name, last name, SIN, address, phone, birth date, salary, department ID. EID is the primary key. Alternate key. All other candidate keys not chosen as a primary key. Foreign key. An attribute in one table that references the primary key of another table, or it can be null. Both foreign and primary keys must be of the same data type. For example, employee EID, first name, last name, SIN, address, phone, birth date, salary, department ID. Department ID is the foreign key. Nulls. This is a special symbol independent of data type, which means either unknown or inapplicable. It does not mean 0 or blank. No data entry. Not permitted in primary key. Should be avoided in other attributes. Can represent an unknown attribute value, a known but missing attribute value, a not applicable condition. Can create problems when functions such as count, average, and sum are used. Can create logical problems when relational tables are linked. The representation of null. Find all employees EMP in sales whose salary plus commission is greater than 30,000. Select EMP from salary table where job name is equal to sales and commission plus salary is greater than 30,000 implies E10 and E12. This result does not include E13 because of the null value in commission. To ensure the row with the null value is included, we need to look at the individual fields. By adding commission and salary for employee E13, the result will be a null value. The solution is shown below. Select EMP from salary table where job name is equal to sales and commission is greater than 30,000, or salary is greater than 30,000, or commission plus salary is greater than 30,000 implies E10 and E12 and E13. Entity types. In this video, we are going to see about entity types. Entity relationship modeling contains several entity types such as existence dependency, weak entities, Strong entities. Existence dependency. An entity's existence is dependent on the existence of the related entity. Its existence is dependent if it has a mandatory foreign key. That is a foreign key attribute that cannot be null. Spouse entity is existence dependent on the employee. Weak entities. These tables are existence dependent. They cannot exist without entity with which it has a relationship. Primary key is derived from the primary key of the parent entity. The spouse table is a weak entity because its primary key is dependent on the employee table. Strong entities. If an entity can exist apart from all of its related entities, it's considered a strong entity. Kernels are strong entities. A table without a foreign key or a table that contains a foreign key which can contain nulls is a strong entity. Relationship. In this video, we are going to see about relationship. These are the glue that holds the tables together. They are used to connect together related information in other tables. One-to-N relationship should be the norm in any relational database design. Relational database norm found in any database environment. For example, one department has many employees. The diagrammatic representation of 1:N relationship. 1:1 relationship. 1:1 relationship is rare in any relational database design. One entity can be related to only one other entity and vice versa. One-to-one relationship indicate that two entities actually belong in the same table. The diagrammatic representation of 1:1 relationship. M:N relationships. Mapping M-N binary relationship type. For each M-N binary relationship, identify two relations A, B represent two entity type participating in R. Create a new relation S to represent R. Include in S as foreign keys the primary keys of A and B and all the simple attributes of R. The combination of primary keys of A and B will make the primary key of S. The diagrammatic representation of M:N relationship. Unary relationships, that is recursive. One in which a relationship exists between occurrences of the same entity set. The two keys, primary key and foreign key, are the same, but they represent two entities of different roles relate to this relationship. In some entities, a separate column can be created that refers to the primary key of the same entity set. Ternary relationships. Mapping ternary relationship type. For each n array greater than 2, relationships create a new relation to represent the relationship. The primary key of the new relation is the combination of the primary keys of the participating entities that hold the n, that is many sides. In most cases of an n-array relationship, all the participating entities hold a many side. The diagrammatic representation of ternary relationships. Relationship strength. Relationship strength is based on how the primary key of a related entity is defined. Weak relationships, non-identifying relationship. Exists if the primary key of the related entity does not contain a primary key component of the parent entity. Customer, customer ID, customer name. Order, order ID, customer ID, date. Strong relationship, identifying. Exists when the primary key of the related entity contains the primary key components of the parent entity. Course, CRS code, department code, description. Class, CRS code, section, class time. ERD, Entity Relationship Diagram. In this video, we are going to see about ERD, that is Entity Relationship Diagram. Another tool for requirement analysis is the Entity Relationship Diagram, often called as ER diagram. It is a detailed logical representation of the data for an organization and uses three main constructs, that is, data entities, relationships, and their associated attributes. Entities. An entity is a fundamental thing of an organization about which data may be maintained. An entity has its own identity which distinguishes it from each entity. An entity type is the description of all entities to which a common definition and common relationships and attributes apply. Consider a university that offers both regular and distance education programs. Program and student are both entity types in this example. Regular and distance education are entities of program, whereas national and international are entities of student. We use capital letters in naming an entity type, and in an ER diagram, the name is placed inside a rectangle representing that entity. The representation of two entity types in an ER diagram. Relationship. In this video, we are going to see about relationship. A relationship is a reason for associating two entity types. These relationships are sometimes called binary relationship because they involve two entity types. Some forms of data model allow more than two entity types to be associated. A student is registered for a program. Relationships are represented by diamond notation in the ER diagram. We consider another example in which a teaching department of a university is interested in tracking which subjects each of its students has completed. This leads to a relationship called completes between the student and subject entity types. As indicated by the arrows, this is a many-to-many relationship. Degree of relationship. The degree of a relationship is the number of entity types that participate in that relationship. Thus, the relationship completes is of degree 2 since there are two entity types, student and subject. The three most common relationships in ER models are unary, that is degree 1, binary, that is degree 2, and ternary, that is degree 3. Unary relationship. Unary relationship is also called recursive relationship. It is a relationship between the instances of one entity type. An instance is a single occurrence of an entity type. For example, there is one student entity type in universities, but there may be hundreds of instances of this entity type in the database. Is married to is one-to-one relationship between instances of the person entity type. That is, each person may be currently married to one other person. In the second example, is friend of is one-to-many relationships between instances of the student entity type. Binary relationship. Binary relationship is a relationship between instances of two entity types and is the most common type of relationship encountered in ER diagrams. The first, that is one-to-one, indicates that a student is assigned a student ID and each student ID is assigned to a student. The second, one-to-many, indicates that a program may have many students and each student belongs to only one program. The third, many-to-many, shows that a student may register for more than one subject and that subject may have many student registrants. The diagrammatic representation of binary relationship. Ternary relationships. Ternary relationship is a simultaneous relationship amongst instances of three entity types. The relationship may have provides the association of three entities, that is teacher, student, and subject. All three entities are many-to-many participants. There may be one or many participants in a ternary relationship. In general, n entities can be related by the same relationship and is known as n-array relationship. Cardinalities and optionality. Suppose that there are two entity types A and B that are connected by a relationship. The cardinality of a relationship is the number of instances of entity B that can be associated with each instance of entity A. Consider the example: a student may register for many subjects. The diagrammatic representation of use of cardinality. The minimum cardinality of a relationship is the minimum number of instances of entity B that may be associated with each instance of entity A. If minimum number of students available for a subject is 0, we say that a subject is an optional participant in the register for a relationship. When the minimum cardinality of a relationship is 1, then we say entity B is a mandatory participant in the relationship. The maximum cardinality is the maximum number of instances. In our example, maximum is many. The modified ER diagram. The 0 through the line near the subject entity means a minimum cardinality of 0, while the crow's foot notation means a many maximum cardinality. Cardinality of relationships. Cardinality of relationships can be used to identify relationships between entity types. Attributes. In this video, we are going to see about attributes. Each entity type has a set of attributes associated with it. An attribute is a property or characteristic of an entity that is interest to the organization. Following are some typical entity types and associated attributes. Student, student ID, student name, address, phone number. Employee, employee ID, employee name, address. We can use an initial capital letter followed by lowercase letters and nouns in naming an attribute. In ER diagram, we can visually represent an attribute by placing its name as an ellipse with a line connecting it to the associated entity. The diagrammatic representation of attributes. Candidate keys and identifier. Every entity type must have an attribute or set of attributes that distinguishes one instance from other instances of the same type. A candidate key is an attribute or combination of attributes that uniquely identifies each instance of an entity type. A candidate key for a student entity type might be student ID. Some entities may have more than one candidate key. One candidate key for employee is employee ID, a second is a combination of employee name and address. If there is more than one candidate, the designer must choose one of the candidate keys as an identifier. An identifier is a candidate key that has been selected to be used as the unique characteristics for an entity type. The diagrammatic representation of identifier. The representation for a student entity type using ER notation. Using entity relationship diagram to represent data is still an important technique today. The data flow diagram and the ER diagram each highlight a different aspect of the same system. As a consequence, there are one-to-one correspondences that must be checked to ensure that an ER diagram and a data flow diagram are consistent over all applications. This suggests that it is desirable to use both methods such that we can view the logical issues from the two perspectives generated by these approaches. DFD, Data Flow Diagram. In this video, we are going to see about DFD, Data Flow Diagram. Data Flow Diagram DFD. A data flow diagram DFD is a tool that depicts the flow of data through a system and the work or processing performed by that system. Synonyms include bubble chart, transformation graph, and process model. A DFD has 4 types of symbols: external entity, process, data flow, data store. External entity. An external entity is a source or a destination of data. Process. A process transforms data from one form to another. This transformation may be logical or physical. Data flow. A data flow is the path over which the data flows as it travels through the system. Data store. A data store represents a place in the DFT where there is a logical requirement for holding data from transaction to transaction. A DFT is used to describe what data flows rather than how it flows. The concern is understanding the transformation that are required to convert the input to output. It is independent of hardware, software, data structure, and file organization. DFDs are drawn at various levels of abstraction. The entire system is represented by the level 0 DFD, which gives the system boundaries and its interactions with the environment. Here, the entire system is depicted as a single process. All its interactions with external entities and the input and the output data flows are depicted. The level 0 DFD is also called the top level DFD or the context diagram. Further details of the system are shown in lower level DFDs. In this way, the process represented as a single process in the level 0 may get expanded as the number of processes in the level 1 DFD with the data flows between them depicted and the data stores also depicted. A level 1 DFD process may again be expanded into its constituent process in a level 2 DFD and so on. Expanding the information into a lower level DFD is also called exploding in DFD. In order to be able to record more information in a DFD, many analysts use the newer symbol set for a DFD. Example of a data flow diagram. Certain rules while drawing DFDs are: all data flows must contain data. If two or more documents travel together, they should be shown as one data flow. All data flows must begin from end at process as a data flow either initiates a process or is the result of a process. There cannot be a data flow directly from one data store to another. In physical DFDs, a process may be required to show routing or forwarding of data that may not change the data. Concepts of normalization. In this video, we are going to see about concepts of normalization. Normalization is a systematic way of ensuring that a database structure is suitable for general-purpose querying and free of certain undesirable characteristics, insertion, update, and deletion anomalies that could lead to a loss of data integrity. For example, let's say we store city, state, and zip code data for customers in the same table as other customer data. With this approach, we keep repeating the city, state, and zip code data for all customers in the same area. Instead of storing the same data again and again, we could normalize the data and create a related table called city. The city table could then store city, state, and zip code along with IDs that relate back to the customer table, and we can eliminate those three columns from the customer table and add the new ID column. Fields are John, Chennai, jncsn1@yahoo.co.in 120432. Maria, Chennai. Mario3@yahoo.com 123421. Jack, Madurai. jacke3@gmail.com 124301. The normal forms. The database community has developed a series of guidelines for ensuring that databases are normalized. In practical application, it will often see 1NF, 2NF, and 3NF along with the occasional 4NF. First normal form 1NF sets the very basic rules for an organized database. Eliminate duplicative columns from the same table. Create separate tables for each group of related data and identify each row with a unique column that is a primary key. These criteria are basically concerned with ensuring that the table is a faithful representation of a relation and that it is free of repeating groups. The diagrammatic representation of 1NF. A design that is unambiguously in 1NF makes use of two tables: a customer name table, a customer telephone number table. The representation of tables. Second normal form, that is 2NF. 1NF is the most basic of normal forms. Each cell in a table must contain only one piece of information and there can be no duplicate rows. A table containing courses that are taken in a certain semester and you have the following data. This is not in 2NF because the fourth column does not rely upon the entire key but only a part of it. The course name is dependent on the course ID but has nothing to do with which semester it is taken in. We have duplicate information, several rows telling us that ID 101 is programming and ID 102 is databases. So we fix that by putting the course name into another table where course ID is the entire key. The representation of second normal form. Third normal form 3NF. 3NF was originally defined by EF Code in 1971. Code's definition states that a table is in 3NF if and only if both of the following conditions hold. The relation R table is in second normal form 2NF. Every non-prime attribute of R is non-transitively dependent, that is, directly dependent on every key of R. Boy-Scout normal form. It is a slightly stronger version of the third normal form 3NF. A table is in Boy-Scout normal form if and only if for every one of its non-trivial functional dependencies X tends to Y, X is a superkey, that is, X is either a candidate key or a superset thereof. Fourth normal form 4NF. Introduced by Ronald Fagan in 1977, 4NF is the next level of normalization after Boy-Scout normal form BCNF. Whereas the second, third, and Boy-Scout normal forms are concerned with functional dependencies, 4NF is concerned with a more general type of dependency known as multivalued dependency. A table is in 4NF if and only if for every one of its non-trivial multivalued dependencies X tends to Y, X is a superkey, that is, X is either a candidate key or a superset thereof. Fifth normal form 5NF. A table is said to be in 5NF if and only if every joint dependency in it is implied by the candidate keys. Example: traveling salesman product availability by brand. The representation of fifth normal form. In that case, it is possible to split the table into 3. The final representation of final fifth normal form. Structured English. In this video, we are going to see about structured English. Most programmers are unaware of the large picture of software, so they only rely on what their managers tell them to do. It is the responsibility of higher software management to provide accurate information to the programmers to develop accurate yet fast code. Other forms of methods which use graph or diagrams may are sometimes interpreted differently by different people. Hence, analysts and designers of the software come up with tools such as structured English. It is nothing but the description of what is required to code and how to code it. Structured English helps the programmer to write error-free code. Here, both structured English and pseudocode tries to mitigate that understanding gap. Structured English uses plain English words in structured programming paradigm. The following are some tokens of structured programming. For example, we take the same example of customer authentication in the online shopping environment. This procedure to authenticate customer can be written in structured English as the code written in structured English is more like day-to-day spoken English. It cannot be implemented directly as a code of software. Structured English is independent of programming language. Decision tree. In this video, we are going to see about decision tree. It is necessary to have an unambiguous and understandable way to document processes. It can be done by the decision tree. A decision tree is a sketch of logical structure which is easy to construct and understand. It is a very useful way of depicting policy in brief. It is a network type of chart. A decision tree has nodes that depict conditions, branches that depict possible paths, and action with the conditions and branches. Here, the policy regarding granting a loan is depicted using a decision tree. As it can be seen, it is easy to construct and grasp, but not practical for situations with large number of conditions and branches. A decision tree has as many branches as their logical alternatives. Representation of decision tree. Advantages of decision tree. Decision tree expresses the logic of if then else in pictorial form. It is useful to express the logic when a value is variable or an action is dependent on nested decision, that is the outcome of another decision. It helps the analyst to identify the actual decision to be made. Disadvantages of decision tree. A large number of branches with many paths will confuse rather than help in analysis. For example, draw a decision tree for policy followed by a company in giving discount to its customers as follows. If transaction is on credit and customer's record is good, the order will be accepted but do not give any discount. If customer's record is not good, do not accept any order. If transaction is on cash and sell amount is more than 100 rupees, discount will be given 20%. If transaction is on cash and sell amount is between 50 and 100 rupees, then discount amount will be 10%. If transaction is on cash and sell amount is less than 50 rupees, order is accepted but no discount will be made. The representation of company policy. Decision table. In this video, we are going to see about decision table. A decision table represents conditions and the respective actions to be taken to address them in a structured tabular format. It is a powerful tool to debug and prevent errors. It helps group similar information into single table, and then by combining tables, it delivers easy and convenient decision making. Creating decision table. To create the decision table, the developer must follow basic 4 steps. Identify all possible conditions to be addressed. Determine actions for all identified conditions. Create maximum possible rules. Define actions for each rule. Decision tables should be verified by end users and can lately be simplified by eliminating duplicate rules and actions. For example, let us take a simple example of day-to-day problem with our internet connectivity. We list all possible problems under column conditions and the prospective actions under column actions. Table is the representation of decision table. Introduction to documentation. In this video, we are going to see about introduction to documentation. Documentation is one of the systems which is used to communicate, instruct, and record the information for any reference or operational purpose. They are very useful for representing the formal flow of the present system. With the help of documentation, it is very easy to track the flow of system's progress, and working of the system can be explained very easily. It helps to provide the clear description of the work done so far. It is essential that the documents prepared must be updated on a regular basis. This will help to trace the progress of work easily. With appropriate and good documentation, it is very easy to understand how aspects of the system will work for the company where the system is to be installed. It also helps to understand the type of data which will be inputted in the system and how the output can be produced. After the system is installed, and if in case the system is not working properly, it will be very easy for the administrator to understand the flow of data in the system with documentation, which will help he or she to correct the flaws and get the system working in no time. Uses of documentation. It facilitates effective communication regarding the system between the technical and the non-technical users. It is very useful in training new users. With a good documentation, new users can easily get acquainted with the flow of the systems. Data Dictionary. In this video, we are going to see about Data Dictionary. Data Dictionary is a centralized collection of information about data. It stores meaning and origin of data, its relationship with other data, data format for usage, etc. Data Dictionary has rigorous definition of all names in order to facilitate user and software designers. Data Dictionary is often referenced as metadata, that is data about data repository. Requirement of Data Dictionary. The data is referenced via Data Dictionary while designing and implementing software. Data Dictionary removes any chances of ambiguity. It helps keeping work of programmers and designers synchronized while using same object reference everywhere in the program. Data Dictionary provides a way of documentation for the complete database system in no place. Validation of DFD is carried out using Data Dictionary. Contents. Data Dictionary should contain information about the following: data flow, data structure, data elements, data stores, data processing. Data flow is described by means of DFDs as studied earlier and represented in algebraic form as described. Table is the representation of algebraic form of DFD. For example, address is equal to house number plus street or area plus city plus state. Course ID is equal to course number plus course name plus course level plus course grades. Data elements. Data elements consist of name and descriptions of data and control items, internal or external data stores, etc. with the following details: primary name, secondary name, that is alias, use case, how and where to use, content description, notation, etc. Supplementary information, preset values, constraints, etc. Data store. It stores the information from where the data enters into the system and exits out of the system. The data store may include files, internal to software, external to software but on the same machine, external to software in the system located on different machine, tables, naming convention, indexing property, data processing. There are two types of data processing: logical as users sees it, physical as software sees it. Recording data descriptions. In this video, we are going to see about recording data descriptions. Before recording this information on a data dictionary, we obtain the information from various levels of DFDs. For external entities, take the data names from level 0 diagrams, complete the data name, description, attribute, process, access and occurrence on the data dictionary sheets. For processes, take the data names from level 2 diagrams, complete the data name, description, access and occurrence on the data dictionary sheets. For data flows, take the data names from any level of diagram, complete all of the columns of the data dictionary sheets if possible. For data stores, take the data names from level 1 and level 2 diagrams, complete all of the columns on the data dictionary sheets if possible. Data name, a meaningful unique name, for example booking, client, payment book. Allies. Several departments may refer to the data by a different name or term. This must be recorded in the data dictionary. Also, in logical data flow diagrams, the data element may be renamed. For example, on a logical DFD, booking details. On a physical DFD, application form. On a logical DFD, money. On a physical DFD, payment. Attribute. What details are held about the data name? For example, client's attributes could include name, address, account number, account balance, etc. Process. The names of the level 2 processes in which the data is used. Valid ranges. Shows the boundaries of the data, for example, 1 pounds to 999 pounds, 1/1/1993 to 31/12/1993. Storage formats. Shows what format the data is in, for example numerical, date, currency, alphabetical, etc.